Now let's see the next part, that is the net head across reaction turbines. That is can be described as the difference in the total head between inlet flange and the tail water level. So if you go back to the previous slide where we see the constructions of a reaction turbine, there we can see these 2 points where the head difference are being identified. So that to mathematically analyze it, let's see the total head, the turbine total head at the inlet and at the outlet. So it is the functions. Yeah, this is back to the Bernoulli equations where we have the pressure divided by density and gravity, and then the kinetic energy part where the velocity to the power of 2 divided by 2 times gravity plus the elevations at that point of the inlet. And then we look at the outlet conditions, or if we go back to the schematic of a reaction turbine, where is the 0 point, the flange, and then the third point below the turbine. And then we get the pressure at that point, again divided by the density and gravity, plus to the velocity at that point, divided by 2 times gravity, and plus the elevations at that point. And as the total head is the difference between the head between inlet and outlet, and we combine them together, and we put the pressure into the same bracket, and then we put the velocity also in the same bracket and the elevation also the same at the same bracket, then we get the head net head across the reaction turbine. So this is the basic equations for the net head, or normally we name it as the total head across the turbine. To further analyze the equations, we assume that as the area at the outlet of the turbine is in the atmospheric condition, therefore P3 is the atmospheric pressure, has the value of atmospheric pressure, and then as the elevations at the outlet is already equal with the datum line, Z3 will be 0. So therefore we can eliminate these two, and then we get this form of equations as the total head, or to further simplify these equations, we can write it down as H1 minus HFP, where HFP is the frictional head drop due to the frictions between, or due to the interactions between the fluids and the pipeline, for example, and H1 is the available head, so to say. So if we go back to the previous slide again, and we can get this the definitions of each variables here, and as H is the total head, and then we can go to the Euler equations to get the Euler head of the reaction turbine. That is the functions of H, the total head, minus the power loss in the draft tube, minus the head loss at the guide vane, and minus the head loss at the runner. Losses in a radial flow turbine can be attributed into 5 sources. First is the mechanical power loss, or in this term we note it down as PM. And then we have PR, that is the runner power losses. And then we have the casing power losses. And then we have the leakage power losses. The last part is PS, or that is the shaft power output. Now let's have a look at the runner power losses, or PR. That is the functions of density, gravity, and QR here is the flow rate through the runner, and HR is the head power loss or head loss at the runner. The second term of the radial flow turbine losses is the leakage power loss or leakage head loss. That is mainly due to the small q here that we can define as the leaking flow rate that pass the runner. And yeah, so small q here is the amount of flow that lost when it passed through the runner, so that we know that q is the actual flow or the total flow, and then we have QR, the flow that passed through the runner, and Q is the leak flow rate. So we put them together and then we get the total flow rate, so to say. And HR here, capital H, is the total head across the runner. So don't get it wrong with the small HR here, which is the head loss. And capital H is the total head across the runner. So this is head loss, and this is total head across the runner. The last part of the losses is the casing power loss. That is mainly due to the frictions and flow separations inside the casing and also in the draft tube. So the casing power loss, or PC, is a function of density, gravity, total flow rate, and HC, that is the head loss at the casing. And by combining this and let's say the first equations with the three equation here, and we put them together, as we know that the power is equal to the density, gravity, Q, and H, or the total head. And then we put the mechanical power loss here, and then we have the runner power loss, we got the casing power loss, and we got the leakage power loss here, plus the shaft power output. And then from this, as we already know all of the sources or all source of losses, we can get the overall efficiency, that is the functions of shaft power output, which is PS, and divided by the fluid power overall at the inlet. So the fluid power available at the inlet, that is the functions of density, gravity, Q, and H, or this one. And the other terms, and as this is the overall efficiency, the other efficiency is the hydraulic efficiency, that is the functions of shaft power output plus the mechanical power loss divided by the fluid power available at the inlet flange, or in this term is equal to density, gravity, flow rate, and total head. Or the maximum hydraulic efficiency can be written as U1 multiplied with Cx1 divided by gravity multiplied with total head. So this is the maximum possible hydraulic efficiency, but this is the theoretical one, and this one is the maximum possible efficiency.